It's better. My name is Ulusahin Sonmez. I'm coming from Istanbul Boğaziçi University. Today I'm going to present you our work on contextual text normalization. Recently, we started to deal with a huge amount of social media text. Here we have example sentence that's taken from Twitter. What may come to our attention is there are some words that are written different than their original forms. As it is difficult for humans to understand the above sentence, it's also difficult for computers to process it. Text normalization is the task of reverting non-standard language into a more standard and easily processable form. It's also of crucial importance to normalize the non-standard tokens before applying another NLP techniques. While it is easier for us to read the normalized version of this text, it's also easier for NLP applications to process the normalized version of social text as well. In a real-world text normalization system, there are two steps. The first one is the detection of the words that requires normalization. We call these words as ill-formed words. After detecting the ill-formed words, the next step is normalizing them to their canonical forms. Our focus in this study is on normalization. However, we also implemented a baseline detection system as well. One other aspect in normalization is that ill-formed words may have different canonical forms depending on the input text. For example, here, the word WER is normalized as were in the first sentence, whereas it's normalized as were in the second. Recently, there has been a growing interest in the text normalization. Several approaches have been proposed for this task. There are statistical methods and machine translation approaches, but most of them are based on supervised methods. And it's really hard to find labeled data for this domain. Since social text has a very dynamic nature, even if we find annotated data or even if we annotate data, it may become outdated very soon. Lexicon-based approaches have been also proposed, but every day new out-of-vocabulary, OOV, in other words, tokens, are introduced. Therefore, the lexicons may become outdated too. Another drawback of lexicon-based approaches is they always produce the same normalization for a given OOV token, whereas the normalization of a specific token may change depending on the input context, as we have seen in the previous slide. Among the lexicon-based approaches, there are also unsupervised methods. Most of them do not use the input context and produce, again, the same normalization depending on the corpus-based information from their training dataset. In order to handle the evolving nature of social media text, we need a system that can correctly normalize the tokens, even they are seen for the first time in our system. We proposed an unsupervised method for contextual text normalization, and our method makes use of large unlabeled social media dataset to model global context information as well as input context information. And it also uses lexical similarity and grammatical features too. In general, our process pipeline has 3 steps. In pre-processing step, we first tokenize and do part of speech tagging of the input text. And for extracting candidates, many other text normalization systems make use of lexical similarity features and some external resources. In addition to those, we propose making use of contextual information from the input text. We extract those contextual similarity features from a contextual word association graph. Now I'm going to give some more detail about that graph, how we construct it, and how we use it to normalize a given text. Contextual word association graph is generated processing a large unlabeled social media corpus. This is a small portion from our graph. The nodes represent post-tagged words, and we have both out-of-vocabulary and in-vocabulary words in our graph. The edges encode relative positions of the post-tagged words. There is a link between two nodes. We put a link between two nodes if they co-occur in our corpus together within a certain distance. For example, for the word smile, since it has been seen together with beautiful as beautiful smile in our corpus, there is a link from beautiful to smile with an edge proportional to their proportional to number of co-occurrences of these two words in our corpus. Another word pairs, for example, with and beautiful, there is an edge between them with a distance 1 because they have been seen together with a distance 1. In other words, when there was one word between them, for example, in the example here, with a beautiful smile or with most beautiful eyes. Given an input text normalized, we make use of the graph to find normalization candidates. And let me show you, let me illustrate this through this example input, where the word beautiful, or beautiful, is misspelled. Candidates are extracted from graph over the neighbors of the OV word. Here, our OV word, out of vocabulary word, is beautiful, and our neighbors are W, A, and smile. And for example, each edge from node A to another edge that has the same part of speech tag as our OV word, which is adjective here, and with the same distance from node A to the OV node, which is 0 here, brings in as a candidate. Here, new, beautiful, and big are brought in by node A because they have adjective as their post-text, same as out of vocabulary word, and they have the same distance from A to the vocabulary word, from neighbor to the out of vocabulary word, beautiful. Same with the W, same with the node W. Broken is extracted from graph as a candidate because it co-occurs together with W with a distance 1 in the corpus, as in the with a broken heart, or with the broken smile, or with some broken something. We use 3 neighbors on the left and 3 neighbors on the right. And the neighbors on the left and neighbors on the right brings in candidates with different edge directions. The neighbors on the left has an edge direction to candidates, whereas the neighbors on the right have an edge direction from candidate to themselves. After finding candidate nodes with corresponding edges, we later score each candidate using its edge weight with the neighbor. Those numbers are the edge weights. And we also use their frequency in our corpus. So far, we extracted some candidates using contextual features, and we also extract candidates using lexical features and from external resources. The next step is finding the correct normalization among all these candidates. We use three metrics. The first one is contextual similarity score. It's calculated using edge weight and frequency scores. Edge weight represents the input context, And frequency represents the global context of the candidate. Lexical similarity score is calculated using longest common subsequent ratio and edit distance. And we gave an external score to each candidate. If they exist in our slang dictionary or in the transliteration table, or otherwise their external score is 0 by default. Now let's see our experiments and results. In our experimental setup, we generated our graph using Stanford's Twitter dataset. And for part of speech tagging, we have used CMU arc tagger, which is a social media specific part of speech tagger. We used two datasets to evaluate our approach. The first dataset is LexNorm, collected by Hanan Baldwin. It's collected using Twitter, and it has been used by most of the previous studies, so we can use it as a benchmark. The second dataset, panel trigram dataset by Panel and Liu. It's also from Twitter, but it's collected using only messages. Those are sent via SMSs. So it's a SMS-like corpus. We run tests using different components of the system. When tested using only lexical similarity as a baseline, the success rate was quite low. And specific to this data set, when we only use external score, the success rate was quite high. And the combination of these two components is our third baseline. And it's very similar to the Hanan Baldwin settings too. Combining our proposed contextual similarity approach with lexical similarity score and external score, we were able to improve on the results of the previous studies. We achieved state-of-the-art precision, and we didn't compromise much from recall. Thereby, we could improve the state-of-the-art F-score as well. And yes, our second data set. There's also a similar pattern in the second data set too. Owing to the data set SMS-like nature and limit on the length of the inputs, it was 3 grams, we may say it's a more difficult data set than the first one. Therefore, the results we obtained were lower than the first data set. Nevertheless, we could obtain improved precision and F-scores on this data set as well. Most of the previous work assumes that ill-formed words in the input text are pre-identified and performs only the second step. Without detection, they just normalize pre-identified ill-formed words. By implementing a baseline ill-formed word detection, we compared our systems with other systems that perform detection. We used tokens from graph with a frequency higher than 20. Those were filtering with the A-spell spell checker. And these are the obtained results. We believe by obtaining a better OV detection approach, these results can be further improved. The overall results show that using both input context and global context helps improving the task of text normalization. To sum up, we proposed an unsupervised graph-based text normalization approach. Besides using lexical and grammatical features, it utilizes both corpus-based and input-based contextual feature of the text. By applying this approach, we achieved obtained state-of-the-art precision and F-scores. And lastly, we have 3 future work directions. Doing a better OV detection for real-world usage, experimenting on different graph sizes to build a fast and more accurate text normalization system, And lastly, the proposed method is language independent other than the post tagger. And we are planning to implement it on morphologically richer languages, maybe like Turkish. And this is the end of my presentation. I want to thank you all for listening, and I can have some questions if you have.
So thank you for the wonderful talk. I guess one, so if I understand correctly, the methodology, you're conditioning it on the part of speech tag and enforcing that it is the token you're substituting in is of the same part of speech tag, and then you're conditioning it on context. Have you done any breakdown of evaluation looking at the relative OOV rate in context? Because if I understand it correctly, you're conditioning on in vocabulary words, or it's also out of vocabulary words in terms of your context modeling. Yes. So as you get more and more out of vocabulary words, the quality of your context features is perhaps going to drop. How does that impact on sort of the relative noise rates in terms of OOV rate around the context of use of your target word?
Actually, we didn't do such. Well, it's a good idea. You mean looking at the portion of OOV words in the input text.
In the context, that's right. Yeah.
Yeah, we didn't do such experiments.
Right.
But the idea behind it to be able to use both in vocabulary and out of vocabulary word in the context, because sometimes you don't have any in vocabulary words around.
Sure. Yep. Other questions? We've still got plenty of time. Michael.
Two little technical questions. You had, in your graph, you had 0 counts. Wouldn't smoothing help?
I couldn't understand.
Would smoothing help? You had 0 counts in your graph, and I remember correctly.
Yes, actually, I was going to point it out. That edge does not exist. It's just for presentation purpose. We don't have any edges with weight 0, and also another to-do thing is to be able to find a way to have less and more informative edges in the graph.
The second little question, you had distance in the graph. Is there a problem with different sentence lengths? Would it could some sort of normalization help?
In the second data set, we had 3 grams, maximum 5 grams. So actually, we had sentences that's shorter. And as you have seen, the accuracy was around 10%, 10% lower than the other data sets. So I believe the longer the sentence, more accurate the contextual features work.
Final questions? Can we start from the first slide, please? The example of where. Okay. Here you want to extract the original form for where, W-E-R. It can be where or etc. What about if you remove all vowels and get the original consonant, let's say? Mm-hmm. Okay? And if you have a corpus that is normalized using the same way by removing all vowels, you can generate all possible transformation for this WER. First, it will be converted to WR after removing the vowels. Okay? And when you look at the normalized corpus using the same way, you can extract that these two letters WR can be WERE or where or whatever. And you use some contextual information to decide which alternative is the correct in this context. Sorry. What do you think? It's a matter of normalizing or removing, let's say, the vowels in the input and building a corpus that is normalized all by removing all vowels. Okay? So in this case, you can match the letters WR with some alternatives from the original corpus. So you will find WERE as one alternative, and where is another alternative, etc. What do you think?
Actually, following the previous work, we already use phonetic similarity. So we just, I think it's missing in the graph, but we bring in lexically similar candidates using also the metaphone algorithm. So those candidates who has W and R in their skeletons are already in our system. I didn't go into detail of those candidates extracted with lexical features, but we followed the previous work, and I think it became a benchmark using edit distance and some phonetic properties to extract candidates. What we are trying to do is, what if there is W and R as something else? And maybe it's not even phonetically close.
So we've got a couple of minutes to questions.
Just a quick thing, what is the computational cost of this method?
Currently, our system is quite slow. But we are planning to fasten it by first changing the backend. We are using currently Python. We will move to the Java, and we use a big graph. And our preliminary test shows that actually smaller graph with smaller amount of tvits. Now we use 1 gigabyte with 600 megabytes of tvit. It actually achieves better results. So that's one of our future work, to find an optimal graph size that's accurate enough and fast enough to do real-time text normalization. And we also use MongoDB to represent the graph. And that's how we handle the big graph.
Time for one last quick question. Perhaps I can ask you. You mentioned as one of the qualities of your proposed method, its ability to do context-sensitive normalization. Have you done any specific evaluation to see how well it differentiates between the same OOV token being mapped to different IV tokens?
Mm-hmm. Unfortunately, the data sets we had were limited, but it's always in our to-do list to annotate a new data set that we can evaluate our work better in the contextual context too.
Sure. Okay, let's thank our speaker.